Assalamu alaikum. Greetings. So this is Dr. Bilal Wajid. So in the last chapter, which was chapter number 1, we introduced the course. We mentioned what are the topics in the course. We talked a little about signals and then images. Now we're going to start chapter number 2. So chapter number 2 predominantly talks about Fourier transform, discrete Fourier transform, and two-dimensional Fourier transform. Now, because we are dealing with images, images are two-dimensional in nature, and they have an x and y coordinate. Therefore, the idea of extending the one-dimensional discrete Fourier transform to a two-dimensional discrete Fourier transform is rather obvious. A small reminder from the previous lecture was that the information present in a signal, the information present in the signal is the same whether you see it in time domain or you see it in frequency domain. The reason we do such transformations is because some information is highlighted in time, whereas other pieces of information are highlighted in frequency, and therefore the need for transformation. Now, there are 4 types. There is the Fourier transform, the Fourier series, discrete time Fourier transform, and the discrete Fourier transform. In all these options, which are visible in the figure, notice that if the signal is continuous and aperiodic meaning that the signal does not repeat itself, then you would use the Fourier transform. If the signal is continuous and periodic, so there is a period, there is a pattern which does repeat itself, then what you use is what is called a Fourier series. In fact, Fourier series can be assumed to be a Fourier transform. It's just that the time period goes to infinity. So then if the time period on the right hand side and the left hand side, t0 and minus t0 approach infinity, then what you have is referred to as a Fourier transform. Now, a discrete time Fourier transform is when the signals are discrete. So if it is aperiodic, you have something which appears like this, but if the signal is periodic, then you have the same pattern repeating itself. And again, you would see, not in this lecture but in the next, properties of discrete Fourier transform and something like circular convolution will be discussed. So which signal you're referring to, or what is your input signal, directly determines the type of transformation you're going to use. Again, the time signals can answer questions like when an event occurs, but it is the frequency domain which addresses questions like how often. Throughout this course and throughout this lecture series, even in this lecture, we will be using this notation. So fx, small f with an x, would be your signal in time domain, and capital F with omega being the symbol for frequency, will be your symbol for the transform of that signal in frequency domain. Now, this is a repetition of the same signal that we discussed, same thing that we discussed 2 slides before. In fact, this is a extension of the discussion on this slide. And here what we are doing is we are showing you how the transformations look like. So the signal is continuous and non-periodic. You can see here it's an integration, and this is the signal x of t. This is the Fourier transform x of f, and you have an integration over here. Now the same thing that you see over here If the signal is periodic, in this case, this is replaced with 1 over time. So this t is your time period. And x of t, in this case, because it's non-periodic, it's considered across the whole time frame. And therefore, the limits of integration are negative infinity to positive infinity. Here, because it is a periodic signal with a time period t, you consider only that component of the signal which is present in one time period. That's why f is also replaced with f naught, which is the inverse of the time period. For discrete, non-periodic, and discrete periodic, we use a discrete Fourier transform. You can see here, because it's a discrete signal, the integration is replaced by a summation, because the signal does not occur throughout the whole time frame. It only occurs at discrete instances. And that's why you don't have x of t, you have x of m. If the signal is periodic, again, notice over here, the same thing is limited over one time period, where n over here is signatory to that time component. So these are the mathematical formulations of this would be your Fourier transform, these two. This is your Fourier transform, this is your Fourier series, part 3. These two are your discrete Fourier transforms. So a Fourier transform, as the previous slide also showed, is you take the signal across the whole instance of time, because you're dealing with aperiodic signals, and you do an integration with the inverse of this exponential. Now this is interesting, and there is good reason for doing this. F here is your frequency variable, hertz, kilohertz, megahertz, and J over here is your complex number or the imaginary number. This is called the analysis equation, in which you're taking the Fourier transform of the signal. Whereas if you take the inverse Fourier transform, this is called the synthesis equation. This guy here, this is your, obviously this guy here is your Fourier transform of gt. So you're integrating it with respect to the exponential. What you have here at the end of this entire integration process is a complex function which has a magnitude and it has a phase. So in other words, and this is interesting to note, and it's important to note, and it's a common mistake students do, is that when you have the signal gt, it's when you make their diagrams, the x-axis is the time domain and the y-axis is the amplitude. Here, if the faculty asks you, tell me and draw me how the Fourier transform looks like, how does the signal looks like in frequency domain, you have to draw two graphs, one for the amplitude with respect to the frequency and one for the phase with respect to the frequency. So you get two separate graphs. Now this is the inverse Fourier transform. Notice here that you have the Fourier transformation, the signal in frequency domain, and you have a plus here. Over here you had a minus. So this is the Fourier transform. This here is the inverse Fourier transform. Now this is an example where you have a signal. Now see how the signal is captured in the frequency domain. So you integrate it. Notice how the signal is captured. What you have as a resultant in frequency domain is in fact a sinc function. Now I'm going to repeat this again. Notice how it's being done. Again, what you're trying to obtain is that the signal in fact is a summation of exponential signals or exponential functions. Now exponential functions we know are From the Euler's formula, we know a sine theta is a summation of two exponential signals. So is cosine theta, which is a sum of two exponential signals. So what we're really doing here, and I want you to notice this animation again, you're trying to figure out what sum of sinusoidal waveforms, again, exponential signals, as per Euler's formula, two exponential signals combine to make one sine wave. And what you'll see here is that we're trying to match what kind of sinusoidal signals collectively make up this type of signal, and what are the frequencies and which amplitudes. What are the frequencies of those sinusoidal waveforms, and what are the amplitudes of the sinusoidal waveforms, so that when you add them all together, you get this waveform. Now I want you to play this again and notice how this builds up. So now notice the signals which are generating here. So there are a bunch of sinusoidal signals, and as you're adding them, this is what you get. Let's go to the next slide. This is the inverse Fourier transform. You have again now a signal in frequency domain. Now let's take the inverse Fourier transform. What it shows here, that given this sinc function, notice this again, how does it reflect in time domain? This is how it reflects in time domain. Here are some examples of signals in time and their frequency component. The delta function is interesting because you see a delta function here. It seemingly has it has a uniform frequency signal. It goes from negative infinity to positive infinity. This is interesting. In fact, the next lecture discusses impulse function and the impulse, and we're going to discuss that over there. This is the previous two animations that were shown here were showing how this signal converts to this and vice versa. This here is the sinc function. Now notice here, this is interesting. Now notice here what you have is a sine wave translated into two signals, one with a positive frequency and one with a negative frequency component. Now this is directly derived from the Euler's formula, and you can just check the formula right now and you'll see that this is how it maps to. These are some other signals here which are representative of how the frequency signal appears in time domain and their equivalent frequency examples. That was the end of lecture on Fourier transform. Again, this particular lecture did not discuss in detail the Fourier transform. It only showed you the synthesis and the analysis equations. They showed you some examples, and they showed you that there is a transformation. Now, this chapter basically talks about, so in the next lecture we will talk about the impulse function, and we will go back to the properties of Fourier transform before touching base with discrete Fourier transform. Thank you very much and have a good day.